Welcome to Lecture 5 of Geometric Physics 1. Today is called the Lie derivative. The reading is Frankel, sections 4.1 through 4.3. For next time we change books to Marsden and Ratiu, chapter 2, sections 1 through 4. Problem set 2 goes out at the end of this class. Everything we have built so far has been static. Today we learn to differentiate along a flow. Lecture 4 closed the geometry review with Stokes and Maxwell. Everything so far has been static. We have forms, the wedge product, the exterior derivative d, and the pullback. None of them move. Today we learn to differentiate along a flow, and the last operator of the quarter arrives. It is called the Lie derivative along a vector field x. It equals d after the interior product with x, plus the interior product with x after d. There are 4 stops. First, the Lie bracket of x and y, and the Lie derivative of a vector field. Second, the Lie derivative of a form, in Cartan's magic formula. Third, differentiating integrals over domains that are themselves moving. Fourth, the mechanics payoff, which is conserved quantities, and Liouville's theorem. Here is the promise for the hour. By the end of it, we will be able to prove that a Hamiltonian flow preserves omega in one line. That line, and nothing else, is why this lecture exists. First, the Lie derivative of a vector field. That means the Lie bracket and what the bracket measures about a pair of flows. To differentiate y at a point P in the direction of x, we have to compare y at the float point with y at P. Those two vectors live in different vector spaces. One sits in the tangent space at the float point, the other in the tangent space at P. Nothing we have built identifies them. The naive fix fails. Write out how the components of y transform under a change of coordinates and differentiate. You get the term a tensor would give, and also a second term carrying second derivatives of the coordinate change. So the partial derivatives of the components of y are not the components of a tensor. There are exactly 2 cures, and this course uses both. You can add structure. A connection supplies the missing identification by fiat, and that is quarter 2. Or you can add nothing, and use the flow of x itself to carry the far tangent space back to P, that is today. The second route is free, and it works on a bare manifold. Its price is that you may only differentiate along x, and the answer depends on the derivatives of x, not merely on its value at P. Here is the definition. For vector fields x and y, the bracket is defined by its action on functions. The bracket applied to f is x of y of f minus y of x of f. At first sight, that is a second-order operator. It is not. The second derivatives cancel. In coordinates, the components of the bracket are x to the j times the partial of y with respect to x to the j minus the same expression with x and y exchanged. So the bracket is again a derivation, and therefore a vector field. Notice that the same antisymmetry kills the unwanted second derivative term we just met. That term was symmetric in x and y, so the difference wipes it out. The bracket is bilinear and antisymmetric, and it satisfies the Jacobi identity. An example. Let x be the partial in x, and let y be x times the partial in y. Their bracket is the partial in y, a direction neither field produces alone. So the vector fields on M with this bracket form an infinite-dimensional Lie algebra. Coordinate fields always commute. A non-zero bracket is therefore an obstruction to being part of a coordinate grid. Now the definition by flows. Let f sub t be the flow of x. The Lie derivative of y along x, evaluated at P, is the derivative at time 0 of the following object. Take y at the float point, and push it back to P along the flow for time minus t. Both terms now sit in the tangent space at P, so the difference quotient makes sense. And the theorem is that the Lie derivative of y along x is exactly the bracket of x and y. The proof is a Taylor expansion. In a chart, the flow is x plus t times x of x plus terms of second order. So the Jacobian of the backward flow is the identity minus t times the matrix of partial derivatives of x. Multiply that matrix by y, evaluate it at the float point, and keep terms of first order in t. What comes out is y at P plus t times x applied to y minus y applied to x. Differentiate at time 0, and the bracket falls out. So the flow definition and the commutator definition are the same definition. That is Frankel, section 4.1a. Let x of t solve the equation x dot equals x of x, now embedded in a smooth family of solutions depending on a second parameter s. The variation field J is the derivative of that family with respect to s at s equal to 0. J measures how neighboring trajectories separate. Differentiate the equation of motion with respect to s and exchange the order of the two derivatives. The time derivative of J equals the matrix of partial derivatives of x evaluated along the trajectory applied to J. That is Jacobi's variational equation, the linearization of the flow along one trajectory. Its solution operator is the derivative of the flow. Here is the link back to the bracket. A vector field y solves the variational equation along every integral curve of x if and only if the lead derivative of y along x vanishes. Differentiating y along the curve gives x applied to y, while the variational equation asks for y applied to x. The discrepancy is precisely the bracket. Every linear stability calculation you have ever done is this equation. Lyapunov exponents, Floquet multipliers, monodromy matrices. Applied to the geodesic flow, it becomes the equation of geodesic deviation, and its inhomogeneity is curvature. Three conditions turn out to be one condition. First, the bracket of x and y is 0. Second, the lead derivative of y along x is 0, which says that y is dragged along unchanged by the flow of x. Third, the two flows commute, wherever both sides are defined. Hold on to that. A vanishing bracket means the two flows can be run in either order. And when the bracket does not vanish, the bracket is itself a flow. Build the commutator loop. Flow along x for a short time, then along y for the same time, then back along x, then back along y. Now shrink that loop to size 1 over n, and repeat it n squared times. In the limit as n grows, you recover the flow of the bracket. So the bracket is generated by tiny loops run very many times. It is a second-order effect harvested at first order. Finally, independent commuting fields can be simultaneously straightened into coordinate fields. The bracket is the complete obstruction to building a grid. That statement, made global, is the Frobenius theorem. Picture two routes out of a point P. On the first route, flow along x for time epsilon, and then along y for time epsilon. On the second route, do the same two steps in the other order. If the quadrilateral closed, both routes would land in the same place. It does not close. In any chart, the two endpoints differ by epsilon squared, times the bracket of x and y at P, plus terms of third order. Take our example again. Let x be the partial derivative in x, and let y be x times the partial derivative in y. Both routes can be computed by hand in one line each. The gap between the endpoints is epsilon squared times the partial derivative in y, which is epsilon squared times the bracket. Exactly, with no error term at all. Now, the reason this picture matters. This is why you can parallel park. Drive and steer are two vector fields whose brackets generate sideways motion, which neither field generates on its own. It is also the shape of every holonomy computation. Transport around a small loop, and the failure to come back is curvature. We meet that again in lectures 28 through 30. Second stop, the lead derivative of a form and the identity that makes the whole subject work, Cartan's magic formula. Forms pull back along anything, so no inverse is needed, and the definition is simpler than before. Let alpha be a k-form, and let f sub t be the flow of x. The lead derivative of alpha along x is the derivative at time 0 of the pullback of alpha by f sub t. 4 properties, all of which we use. On functions, the lead derivative of f along x is just x applied to f. On a wedge product, it obeys Leibniz, so the lead derivative is a derivation of degree 0. It commutes with the exterior derivative d, and it obeys a Leibniz rule when a form is evaluated on vector fields with a bracket in every slot. That last property, applied to a 1 form, gives the formula you will use constantly. The lead derivative of alpha along x, evaluated on y, is x applied to alpha of y, minus alpha evaluated on the bracket of x and y. Every one of these is an infinitesimal version of a property of the pullback. The third holds because the pullback commutes with d, proved in lecture 3, and because the Lie derivative is the time derivative of the pullback. Here is the theorem, and it is the center of the lecture. For every vector field x, and on forms of every degree, the Lie derivative along x equals d after the interior product with x plus the interior product with x after d. The proof has 4 steps. Call the right-hand side d step 1. The exterior derivative is an antiderivation of degree plus 1, and the interior product is an antiderivation of degree minus 1. So their graded commutator d is a derivation of degree 0. The Lie derivative is 1, 2. Step 2, both commute with d, because d of d is 0. Step 3, they agree on functions. Step 4, locally, every k-form is a sum of terms built from functions and their differentials. 2 degree 0 derivations that commute with d and agree on functions therefore agree everywhere. Now look at what the two sides are. The left is defined by a limit of flows. The right is pure algebra, built from d and a contraction. Cartan's formula converts every question about dragging along a flow into a question you can answer without solving a single differential equation. That trade is the content of this lecture. Let us verify the formula on a one form. Every one form is locally a sum of terms f times dg. Apply d first, and then the interior product, and then the other way round. Add the two lines. Two terms cancel, and what survives is exactly the Lie derivative of f dg. Two examples. First, divergence. Let mu be a volume form. Since d of mu vanishes, Cartan gives the Lie derivative of mu as d of the interior product of x with mu, which is the divergence of x times mu. So divergence needs no metric, and the flow preserves volume exactly when the divergence vanishes. Second, take x to be the radial dilation field in the plane, and alpha the area form. The interior product is x dy minus y dx, whose exterior derivative is twice the area form. So the Lie derivative of alpha is 2 alpha, and areas grow like e to the 2t. The interior product arrived in lecture 4 as bookkeeping. Cartan's formula reveals what it is really for. It is the half of the Lie derivative that carries the vector field. 3 consequences fall straight out. The Lie derivative commutes with d. The commutator of a Lie derivative and an interior product is the interior product with the bracket. The commutator of 2 Lie derivatives is the Lie derivative of the bracket. So sending a vector field to its Lie derivative is a Lie algebra homomorphism. Now the lemma that matters. If alpha is closed, Cartan's formula collapses to a single term. The Lie derivative of alpha along x equals d of the interior product of x with alpha. So the Lie derivative of a closed form is exact, with an explicit primitive. 2 places that lemma is about to do all the work. In lecture 7, omega is closed, and the interior product of x sub h with omega is dh. So the Lie derivative of omega is d of dh, which vanishes and Hamiltonian flows are symplectic. In lecture 9, run the same algebra along a contraction of a star-shaped region and integrate in time. You get the homotopy formula, and hence the Poincaré lemma. Moser's argument for Darboux's theorem is the same trick again. Closed forms are the ones whose Lie derivatives you can integrate. Everything canonical in mechanics descends from that single sentence. Third stop. Differentiating integrals whose domain of integration is itself being carried along by a flow. Let S be a compact-oriented k-dimensional chain. Let alpha be a k-form, and let f sub t be the flow of x. The transport theorem says this. The time derivative of the integral of alpha over the moving image of S equals the integral of the Lie derivative of alpha along x over that same moving image. The proof is 3 lines. Change variables once and for all. The integral of alpha over the moving image equals the integral over the fixed S of the pullback of alpha. The group law for flows gives the time derivative of that pullback as the pullback of the Lie derivative. And S is now fixed, so the time derivative passes under the integral sign. Then feed in Cartan's formula and apply Stokes. The answer splits into 2 physically distinct pieces. One is the integral of the interior product of x with d alpha over the moving region. That piece is creation inside. The other is the integral of the interior product of x with alpha over the moving boundary. That piece is flux through the boundary. Every conservation law in continuum mechanics has this shape. Now let both the form and the field depend on time. We have a family of k-forms alpha sub t and a time-dependent vector field x sub t whose integral curves generate the evolution maps. The theorem gains one term. The time derivative of the integral over the moving domain equals the integral of the partial time derivative of alpha sub t plus the Lie derivative of alpha sub t along x sub t. Why two terms? Because two independent things are changing. The integrand changes, and the domain moves. For a clean derivation, work on M cross the real line with the suspended field, the partial in t plus x. The theorem we just proved, applied up there, gives exactly those two terms. Look at the operator that appeared. On functions, it is the familiar convective derivative. On a one form, it also differentiates the direction, and on a top form, the volume. So the material derivative of continuum mechanics is the partial in t plus the Lie derivative. The version in every fluids textbook is only its action on scalars. The extra terms people find mysterious in the tensor case are the rest of the Lie derivative. Now we specialize. Work in R3 with a volume form mu, a fluid velocity v, and a region carried by the fluid. Take alpha to be a function f times mu. Cartan gives the Lie derivative of f mu as the divergence of fv times mu. Substitute that into the transport theorem. The time derivative of the integral of f over the moving region equals the integral of the partial time derivative of f plus the divergence of f times v. That is the Reynolds transport theorem in one line of algebra rather than a page of Jacobians. Set f equal to the density rho and demand that mass be conserved for every initial region. Out drops the continuity equation. One more, for an ideal incompressible fluid, Euler's equation says the acceleration is minus the gradient of the pressure. The Lie derivative of the velocity one form along v is the convective term plus 1/2 d of the speed squared. Feed that into the transport theorem for a loop carried by the fluid. The right-hand side becomes the integral of an exact form around a closed loop, which vanishes. Circulation is conserved. That is Kelvin's circulation theorem. Last stop, and the reason for the whole hour. What the Lie derivative does for mechanics. Anticipating Lecture 7, work on T star q with omega equal to dq wedge dp. Define the Hamiltonian vector field x sub h by the condition that the interior product of x sub h with omega equals dh. In coordinates, that one condition unpacks into Hamilton's equations in their usual form. Now let f be any function on phase space. Along the flow, the time derivative of f is the Lie derivative of f along x sub h, and that Lie derivative is the Poisson bracket of f with h. So f is a constant of the motion exactly when its Lie derivative along x sub h vanishes. Two instances come for free. First, energy. The Lie derivative of h along x sub h is omega evaluated on x sub h twice, which is 0 by antisymmetry. Second, if h does not depend on some coordinate, the matching momentum is conserved. A conserved quantity is a function annihilated by a Lie derivative. A symmetry is a vector field annihilating h. Noether's theorem is the statement that these are the same equation, read from the two ends. We will make that precise with momentum maps. We do not yet have the vocabulary to state the next theorem properly, that is, Lecture 7. But we can already write its whole proof. Assume just two things. d omega is 0, and the interior product of x sub h with omega is d8. Now apply Cartan's formula to omega. The first term is the interior product of x sub h with d omega, and it dies because omega is closed. The second term is d of dh, and it dies because d of d is 0. So the Lie derivative of omega vanishes. The time derivative of the pullback of omega is therefore 0, and it starts at omega. So Hamiltonian flows preserve omega for all time. The Lie derivative is a derivation, so it kills every power of omega 2. Take capital lambda, the phase space volume of Lecture 4. Its Lie derivative vanishes, so by the transport theorem phase space volume is constant along the motion. That is, Liouville's theorem. Notice what the proof did not use. No coordinates, no Hamilton's equations, no computation at all. 2 hypotheses and 1 identity, and the most used fact in statistical mechanics falls out. That is, the return on today's investment. 7 things from today. 1. The partial derivatives of a vector field are not a tensor. The flow of x repairs that for free, and the repair is the bracket. 2. The bracket measures the failure of 2 flows to commute at second order in the step size. It vanishes exactly when the flows commute. 3. Along a trajectory, a vanishing Lie derivative is Jacobi's variational equation, the linearization of the flow. 4. On forms, the Lie derivative is a degree 0 derivation commuting with d, and it equals d after the interior product plus the interior product after d. That is Cartan's magic formula. And it turns a statement about flows into a statement about algebra. 5. Hence, if alpha is closed, its Lie derivative is exact. 6. The derivative of an integral over a moving domain is the integral of the partial time derivative plus the Lie derivative. That single line is Reynolds' transport, the continuity equation, and Kelvin's circulation theorem. 7. A vanishing Lie derivative of f is conservation. A vanishing Lie derivative of omega is symplecticity. A vanishing Lie derivative of capital lambda is Liouville. Next time we change books to Marsden and Ratiu, Chapter 2, Symplectic Linear Algebra, Canonical Transformations, and Hamilton's Equations on a Linear Symplectic Space. It is deliberately the flat case, so that Lecture 7 can globalize it.